for reminding me. Okay, so the objective, what we should achieve throughout our Module 7 is to develop a description of deadlock which prevent set of concurrent processes from completing their task. So you still remember our previous module, synchronization, which is you should have like might be two process. So you will run it concurrently, so it's going to be a problem also. So you have several methods to solve it. So in this deadlock, you're going to prevent a set on concurrent process. The second one is to present a number of different methods. So this is all the method for you to prevent or might be to avoid deadlock in your computer system. So in our computer system, which is a system model, why actually later on you're going to have a deadlock. So system consists of resources. You're going to have a lot of resources. Resource type like R1, R2, until, etc. So you have a lot, right? If you still remember in your COA subject also, you learn a lot of resources under your system. So example is as CPU cycle. Remember your CPU cycle, memory space, input, output device. So CPU cycle, you also already learned in your COA subject. So each resource type R has W instance. So this is the correlation between your resource and also there will be a W instance. So how long it's going to be took. If a system has two CPU, so let's say you have a CPU, two CPU. Last time you have two processors, but now you can see you are dealing with a system. So you have two CPU, then the resource type CPU has two instances. So you have two instances. Resources type printer may have 5 instances. So you have a lot of resources in actually in your computer. So one of example is printer. It have 5 instances. So you will look into what all the instances for each resources that you are having in your actually CPU or in your computer system. So each process utilize a resource. So you have a several resource. First is request, use and release. It quite similar in our normal activities, like also your previous scheduling. You need to request to enter the CS if you still remember. Then of course you can enter. So you enter. Enter is similar like you execute, you use. After that, after you finish, then you're going to exit. Exit also similar to release. So these three type is like our normal activities also in day-to-day activities. Similar also in your processes and your system. So in our system model, we have three, which is request, use, and release. So let's see what resources can be. Whether it is physically that you can see, like a printer, like your disk drive. So you can see it directly. It's under a resources. It's a physical resources. You have another one more type of resources, which is logical resources. So logical resources is kind of resources, example as a record in your database. You cannot see it physically, but you know it's there, it's logical that you have a database. In terms of a method also, it is some sort of resources for you to prevent any what we call last time we have a lot of problem when we run a process together, and to prevent all the problem we have a methods of semaphore monitors. So this is a logical resources. So two type of resources. So resources are partitions into several types. Each consists of some number of identical instances. So this one is also quite similar to previous slide information. Okay, next you can see here a process must or may utilize a resource in only a following order, which is the three things just now you learned, which is on the resources utilization. This is the basic and general process. So you may utilize this first of all in a request. What is request in our resources? If the request cannot be granted immediately, then the request process must wait until it can acquire the resource. So this is the normal process that you've been through along of OS subject. Whenever you try to go into something like say our previous module, you try to go into the CS, you cannot interrupt. So what you need to do, you need to wait until the process inside, let's say process A, finish or exit first. After it exit, then you can enter. So your process B need to wait. This is a normal process that you already learned. So while you are requesting, you need to check granted a permission from any system that you want to accomplish with. So you must wait until you were given a granted or permission. Second, use. Use is the process can operate on the resource. So your process can operate means that you can execute the process. You can start the process. You can enter into CS. So it is under use. And lastly, release means that it's the process release the resources. So you're going to exit, you're going to end the program. This is the similar meaning for each of these three. So let's see under deadlock. Deadlock is our general and our topic for chapter 7. So you need to know how and why deadlock will be occur. So deadlock is a state when every process in set of processes is waiting for an event that can be caused only by another process in the set. So this is the definitions of deadlock. So you need to remember, although there is a lot of other definition when you try to Google, but basically the meanings is nearly the same. But please make sure you refer your slide or your reference books that I provided in the e-learning. Many programs completing for a limited resources. You know that every program have their own resources. So example, a system has 2 CD drive. I don't know whether I think a system, not a computer. So might be a system quite huge. It is not just a normal our personal computer. So that's why you have 2 drivers here. So let's say a system has 2 drivers. So this is one example. And process 1 and process 2 each hold 1 CD drive. And each need another one. So of course you cannot run simultaneously. Although you said, okay, I'm going to run P1 and P2. You're going to need these both. But of course, you're going to wait one another to do a process. As long as for here, P1 and P2 need another one. So if one is like broken might be, so you cannot continue. So one more thing, another example, which is our traffic jams. If let's say you can say this one need this lorry, this car need this lorry. If this lorry didn't move, so you just start here. So that is a deadlock, which is you wait for event, let's say, to start, which is you still need others process to start, so it will be occur. So you need this lorry to start moving. If this one not moving toward here, so you cannot also move forward. Similar also, this one need this or this one need this, so it can move around. So in our deadlock, each process is a set of process waiting. So you need to wait for an event that can be caused by another process. So you wait as a car, you wait for the lorry to move. So that is deadlock. You can see here there is a lot of traffic jam. For this lorry, if you want to move, you need this van to moving forward. If no, all of the car will be stuck. Okay, this one is a waiting. This will be waiting for you to move. The move is an event. Okay, so you wait for an event which is to move. That will be caused by another process, which is if you are a van there, you need the lorry to move, caused by another process. So similar also example of this traffic jam. So a lot of other example that you can see on Deadlock. So here, let's say you have a process A and process B. And your resources is X and Y. A hold X, waiting for Y. So you're going to wait for Y. Okay, let's see here the picture. This is the example for this process A and process B. So this process A are holding the X, and it wait for Y to start. While for B, it's going to hold the Y and it wait for the X to start. So let's say this is a roundabout in our road. So you cannot move unless this, okay, for A to move, which is to bring X here. So you need to wait for a while to move. So it is a process for you to wait each other. Similar also for B, you need to wait for X to move. So that will be a correlation of the process. And you can see here in terms of memory, memory is a usability resources. Total memory is 200 kilobyte. Let's say you have a total of 200 kilobyte. So you're going to have several process, which is process 1 and process 2. First of all, you want to request 80 kilobyte. So this is your process 1. You want to request a 80 kilobyte for your from your memory 1. Then you have process 2. You want to request another 80 kilobyte. Altogether is 180 kilobyte. So you have it is still enough for you because it is total of memory is 200k. So what will happen? Might be you need to wait a request. So supposedly it's going to be 80, which is you request 80, right? So you're going to wait to memory to give you and provide you with 80 kilobyte, which is M is a message, a consumables resource that you're going to use to request. P1 receive M2 from P2, which is message from M2, and then P2 receive M1, message M1 from P1, process 1. Okay, so P2 receive message 1 from your process 1, while P1 receive message 2 from P2. So this is how you're going to get, and you're going to need to wait for the request. So let's say after you have request, you request another. So you're going to wait because sometimes it's not enough because it's already more than 200 kilobyte. So you need to wait until like empty space are given for you. So that is about the introduction of deadlock. How deadlock, what is the deadlock? What is the example of deadlock? Now we will see the characteristic detail on deadlock. So deadlock can arise in 4 conditions, which is hold simultaneously. First that you need to remember about deadlock is mutual exclusion. Second, hold and wait. Third, no preemptions. And circular wait. So about the first condition that deadlock can occur, which is mutual exclusion, only one process at time can use a resource. So you need to have only one resource or for the one process. So although you have a lot of processes, a lot of resources, only let's say you have P1, P2, P3, you have a lot of other also resources, let's say. So maybe you want to get resources here. So P1, P2, P3 try to get this resource, but only one will be granted to process, to use the resource. Second one is hold and wait. Hold and wait is a process holding at least one resource in your waiting to acquire additional resources held by other processes. So it's going to be, let's say P1 are using R1. So you're going to process holding at for one resources, which is you are waiting to use the resources that hold by others. So let's say P2 hold this as a waiting, but this one are used by P1, so you wait. So another one, let's say P3, you're not going to be wait because this P2 already put that is going to be waiting. And the third one, no preemptions, which is a resource can be released only voluntarily by the process holding it after process has completed its task. So it is a release automatically by a process that hold it, so because it's already finished. So let's say P1 hold R1, and then it will be release the R1 because it's already done, finished, and it's going to be complete. That's why it just release it. And lastly, circular wait. For circular wait, there exists a set. Let's say you have a lot of processes of waiting processes, just as P0 waiting for resource that held by P1. P0 waiting resources, let's say the resource is RA. So this is held by P1. So you want to wait. While P1 is waiting a resource that held by P2. So it is, So P2 hold RB. So this one wait for this RA. P1 wait for RB. Resource that held by P2. So it will continue, which is, let's say later on you have another RC. This one is hold by P3, but P2 want and wait for RC. So it is a correlation, which is circular waiting. And lastly, you can see here for PN is waiting for resource that held by 0, and it will circular. That's why it's set a circular. And lastly, you have PN. PO still have let's say RN here. It hold RN. PN got their own R, N plus 1, let's say it's hold this, but this is waiting for Rn, so it will be circle. So you can try to see what is the differentiation for these 4 things that might occur a deadlock. So another one more thing you can see here under deadlock activity. Just now you see on the condition how deadlock will be occur. Now we see on the activity. This example is about car deadlock in an intersection. So you have here car A. This one is resources you want to go. This is car D, car C, car B. B want to move to Z, but it need to wait, of course, I guess here for X to finish. So it's wait for X. It wait for C to do the X. So it will be coloration. You can see it's look like a circle also. If we assume that process equal to vehicle, so a process equal to vehicle and resources is equal the road. So this is all the resource or a road. Answer the following based on the figure. What are processes? So which one is a processes? What are resources? The X, Y, Z, W, X, Y, Z. How does deadlock occur? Explain how 4 deadlock conditions are applied in the gridlock. Mutual, whole, no preemption, and circulation. When you use this and try to relate with the situation. How to prevent deadlock? This one we still not yet learn. Might be we still need to figure out, because there is things that we just find out, okay, this is the thing that occur deadlock. 5, from this, if you already know the algorithm, for algorithm, right, you learn, right, you're going to learn on prevention deadlock. So from this, which condition is being prevented and how? So question number 4, 5, you will learn after this. So let's see for the first one under resource allocation, which is RAG, resource allocation graph, RAG. You're going to relate to a set of verticals V and a set of H we will use as a E. V is a partition into 2 types. So you can divide it into 2 types, which is a process and a resource. So a process, of course, you know 1, 2, 3 until n, the set consisting of all processes in the system. While the R here, R is resources, the set of consisting of all resources type in the system. Then you need to have also like a message for you to send a request. You're going to colorate and corresponding to your age. Request age which is directed age between your process and also resource. Another one is assignment age, which is directed your resource to your process. See this example. We use our picture, a simple symbol for you to see on the process later on. We will use in the picture. So process will be using like a circle like this. Resources start with 4 instance. So you have a resource look like a box here, and inside the box you have 4 boxes inside. So it is a resource with 4 instances. P1, which is process request instance of RJ. This is our resource. And P1 is holding an instance of RJ. So type of age, you can see here, let's say example P1 try to request resource from R1. Okay, I guess maybe we will continue this example after this. We have a 5-minute break first, okay? Is it okay? Anyone? We have a break first and then we continue, okay? For this example under our resource allocation graph.
Okay, doctor.
Okay, thank you. Okay, class, let's continue back with our class. So let's redo back a recap just now so that we're going to start back with our RAG. Okay, can I continue?
Yes, sir.
Okay, so just now we look into the resource allocation graph. We have V verticals and also H. We take a look into there is two type of verticals, which is process and resource. And there is two type of H, which is request H and assignment H. On the request H, it will be a directed H from your process to resource, while assignment H, which is directed H from resource to process. So here there will be an example for you how you're going to draw for a process, for a resource, and when you have a process request resources, when you have a process holding your resource. So if you request a resource, it is pointing like this. If you hold, it's pointing into your process. So if you, this one, hold. If you hold the process, if you request a process. So in this picture, it shows you the type of H. You just only have two types, which is request H or assignment H. And you're going to use these pictures to show up. So you know already, like a box here square, you're going to have, this one is a resource. And this circle one is a process. So this is a process. Now you can see here, it is under request H, which is you are request from your P1 request a resource from resource 1. So it a request H. Well, another one you have what? Another one you have assignment H. Assignment H means that your process 1 or your process I hold the resource J. So you have here assignment H. The picture already changing. You can see here, this is resource, this is process now. And the arrow pointing like into the process, so it means that it's hold the resource. So you're going to have this resource is assigned to the process, means that process hold this resource. Similar, vice versa, whether you can just like mentions that resource assigned to a process or process hold the resource. Assignment H is directed H, which is resource was assigned to the process. So it's depend on what process. Okay, let's take a look more example. Example of RAG. So in this picture, before that, maybe I can give you an example. Let's say you have okay, you know that for this part, what is happened here? This is mentioned, it is a assignment each. What assignment each? This resource 1 are assigned to P1 or P1 whole R1. For this part, it is a request each. This is a request each because P1 process 1 request R2. So it is a request each. Well, for this part, it is a assignment each, P2 whole R2. And lastly here it is a request each, which is P2 request R1. So this is the basic differentiation on how you can see whether it is a request age or it is a assignment age. Okay, now example, we back to this example, which is under RAG. You have here 3 process. And you can see here what is the difference between all of these arrow. Which one is the request age and which one is assignment age? Similar also at here and here. So in this you can see there is a difference, which is in this picture, just at the page 12 here, you have resource start with 4 instance. So you can see here you can use and draw boxes or you can draw a dot like this. So in this picture for R1 only have one instance, it's going to have one. Similar also with R3. While R2 you have 2 instances. R4 you have 3, but no one requests for R4. So there is no communication for R4, isn't it? So here P1 requests R1. So you can see here how the arrow look like. It's going to be RE. P1 requests for R1. Well, for this part, it is AE, assignment each. This one is RE, this one is AE, this one is AE. Okay, there is a difference. You can see from this. P1 is request R1. R1 is whole or assigned, okay? It's assigned by P2. P2 requests R3 and R3 assigned or whole, which is for P3. You see here? So you finish already at this. You can see that when you have only one instance, you can only handle one process. But when you go at the down part here, although it is one resource, but it hold or it assign to process. You can see here, it hold by R2 holds or assigned by P1N. So there is N here, P2. Why? Because it got 2 instances, so it can serve 2 process. If you have 3, you can serve 3 processes in one time. If you have 4, you can request 4 processes in one time. So this is the basic information about the process, resource with instances in terms of the request age and assignment age. So you need to know how to draw, or might be if you cannot, if you were not asked how to draw, you will know and need to know also in terms of the picture which one is request H, which one is assignment H. So you need to know the meaning also. Okay, there is a lot of other example. Let's see here. Several instances of resources. You have one instance, two instances, and three instances. So I don't know yet because there is no error. Let's see the error now. Okay, now we can see here what is actually happened. You already know about a request H and assignment H, especially when the error where it points to. From R to P, what is the meaning? From R to P, it is assignment H. From P to R, what is the H? So from here, if you were given with this like picture, so you know what is actually happened. So let's say we look one by one. For process 1, it's whole R2. Process 2, it hold two things. You can see here, it hold R2, it hold R1. And lastly, process 3, hold R3. So this is under process state that you can see which one are holding the resources which. So P3 hold R3, P2 hold R1, and R2, P1 hold R2. You see the pointing of the arrow. So now you can see here that one is what? Assignment H. Just now, okay? Assignment H, assignment H, assignment H, assignment H. So we assume this black color arrow, I didn't change the color, is as assignment H. While after this you have that dot, 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 dot. It is a request H. So let's see here. When you have a request H, still under process state, now you continues. Just now P1 whole R2, you done this part. And because you can see under P1, it also requests for R1. It requests R1. So request means also waits. It's going to wait R1 because just now R1 is hold by P2, so you cannot use it because it's only have one instance. You cannot use parallelly simultaneously with P2, so you need to wait until P2 is finished. After that, you can see here another RE. RE is request each. So P2 wait for R3, which is hold by P3. So it's hold or it requests. Okay, it requests R3. So that is on the example 1 here. So in terms of symbol, this is on the sentences of the process state. In terms of symbol, you can see here, you have P as a process, R as a resources, E as a H. So what is the H process here? So there will be a differentiation between from where to where for the arrow. Okay, from where to where for the arrow. Let's see first one by one. If it's weight, then it's going to pointing to the resource. While if it's whole, it's going to be pointing like this. Mean R2 will be pointing to P1. So for the first sentences here, it will be these two. you have sorry, you can see here P process, you have 3 process, but for R you have only 3. Why? Because there is no need for you to explain on R4, because R4 is not even hold by any process, not even request by any process. That's why you have only 3 here. Okay, we continue here, P2 whole R2. So it's going to be pointing like this for the arrow. P2 R1. Sorry, this one is R1. Okay, so R1, P2 R1, it is here. Yeah. So this one for this. And another one is R2, means that P2 whole R2. Or you can change it as P2 R2 P2. So it will be here. And lastly, P2 wait. Okay, wait for a R3. P2 R3. So it give you example in the colors also. For this, it is a request or a wait. For the black color one is a assignment age. It is a hold or assign. So that is in terms of RAG. Is it okay? A sample. This one is very simple, easy for you to understand. I guess it is not too hard for you to memorize about how you're going to use the symbol, about how you're going to define whether it is a request S or might be assignment age. And if you were given with the picture also, I think that it's easier for you to also get the process stage. What is actually happened in the picture, isn't it? It is not too hard, right? So now let's see and move to another one, which is basic faith. So here, if a graph content of no cycle, means that no deadlock. If graph content a cycle, if only one instant per resource type, then deadlock exists. This one is a fact. And if several instances per resources type, then possibilities of deadlock. Might be it is a possible, okay? It is possibilities of deadlock. But this one is deadlock exists, which is must exist. This one is having a possibilities. So no cycle, no deadlock. What is the example like this? There is no cycle. There is no correlation between each other. So you're not going to wait any others. So there is no term of waiting. That's why there is no deadlock for no cycles. For B here, you're going to see there is a cycle things, but it depends also in terms of instances inside the resource. If it's only one, just now like a dot, right? If only one, then you need to wait. If two, like if two, right, resource two have two, so it can serve both. So it is not going to occur a deadlock because there is no waiting, because you can directly serve. So there is a possibilities if it is have several instances, but maybe you have another request from P3. So there is a possibilities. Now if they have 3, then it exists the deadlock. So you need to memorize the basic facts here. Okay, is there a deadlock in the picture for this resource allocation graph with circle? So here, if you wait here, okay, for waiting here, is it have a deadlock or not? So of course it's going to be have a deadlock because you request and wait for others unless there is another instances. But you can see, imagine if you have only one instance per resource type, then deadlock exists. So let's see another example. So it's more complicated now. You can see just now there is no this request, but it is having now. So how about the process state? So the process state now, you have exist two cycle, one like this, I guess, one like this. So here similar, this one is all similar thing as example one just now. So no need for us to continue back what is happened just now, we already look into, but you add another one RE request H here. So for this request H, it's going to be P3, just now P3 whole R3, yeah, okay. P3 the whole R3. Now P3 wait or request R2. R2 only have two instances, that's why you need to wait. If there is a 3, then this one will be directly pointing like this with the black color. But now only 2, so you can only process P1 and P2. P3 need to wait. P3 requests a R2. P3, where is P3? P3 requests R2. So P1, P2, P3 are in a deadlock state because they are waiting for one another to finish. So for this part, is there any deadlock? P1 request R1. R1 is held by P2. R1 is held by P3. P3 request R2. Okay, is there any deadlock for this? So let's see the example now. Maybe you can try to think whether it's having a deadlock or not, because it's having also a request there. So you can see about the cycle. So there is a cycle, and which one are having a waiting, which is you need to also have a waiting process before you can start, means that you are having a deadlock. So let's see here, P1 requires a R1. So the RAG has one cycle like this, I guess. But here also, let's see, okay. P1 request R1. So this is, and then you are having this one, it have two instances. So let's see here, it is then hold for the R1 is held by P3. It also hold by P2, but P2 did not request anything. So no need for you to figure out anymore because it is not a cycle. So this is request a P3, then request the R2. So it's a request R2, and R2 is held by P1. So only one cycle here. This one is direct. Like this. It is direct. This is direct. So it is not cycle. The only cycle is like this. So which one is having the deadlock? P1 and P3 only that are contained in the deadlock state. So the system is the full system. The full system is not deadlocked. When P4 release R2, the resource can be assigned to P3. So if let's say you finish this, so you will directly put like this, the black color. So no waiting anymore. It is one direct. So there is no cycle continuous. Okay. However, the system is not deadlocked when P4 is released, or might be also P2 is released. So that there is no more cycle. Or another one more thing, if let's say P2 is released, so it's going to be pointing like this, R1 to P1. So there is no more also waiting for P1. So only P3, which is having a request, but it is not a cycle. So there is no deadlock. Okay, this one is just a condition. If let's say it's already released, so you have a possibilities of not having the deadlock anymore. So any question for this part? I guess this one is much more interested if compared to all the meaning, the theory of the algorithm, the definition. So I think in terms of understanding the algorithm for RAG is much more interested. You need to know how to differentiate between request age, assignment age, how also to see the process state, and after that you need to also know how to check whether you are having the deadlock or not, and which of these processes are dealing with deadlock, and when the deadlock will be finished. Also, is there any possibilities of getting the deadlock to finish, which is like this example number 3. So is it okay? It's okay.
I think it's okay.
It's quite interested, I guess, for this deadlock things. Uh, and I guess if question also you can easily answer, right? The question is just asking like about the deadlock, about the process, so you need to know the differentiation only, isn't it? Okay, we move to another subtopic, which is method for handling deadlock. So after that, after you see all the problem, you know already how the deadlock will be occur, and uh, about the facts on deadlock. So you know there is a problem when deadlock occur. We need to wait. So it's also going to take and gain a lot of things later on. So you need to have an algorithm or method for you to handle if the deadlock is occur. So last time in your beginning slide, you see that there is a 4 possible methods for you to prevent, to avoid, to handle actually the deadlock. So ensure that a system never enter deadlock stage, which is deadlock preventions, deadlock avoidance. These two methods is going to ensure that your system will never enter deadlock state. So these two methods. Another one is allow the system to enter deadlock state and then recover. That's why you can see there is a recovery from deadlock. Okay, so you have 4 things to handle deadlock, and one more. And one more is ignore the problem, pretend that deadlock never occur in the system, which is you're going to use the most operating system, which is also similar or include the Unix. So let's see the picture of this diagram, the methods for you to handle deadlock. First, you have the preventions. Second, you have the avoidance. And then third, you have the detection and recovery. Lastly, you just ignore. So this is the 4 methods that you need to handle on deadlock. This one is not a solving, but you just ignore. So under avoidance, you have the RAG just now, RAG, and also Banker's algorithm. Under Banker algorithm, you have a safety algorithm and resource request algorithm. On the detection just now also we learned on RAG. By using RAG, you can detect whether the system are having the deadlock or not, isn't it? And there is another detection algorithm, which is the deadlock detection algorithm. So if fail any of these 4 conditions simultaneously arrive using deadlock, what is this? It is a mutual exclusion, hold and wait, no preemptions, and secular waiting for the preventions methods. And under your recovery, there will be a process terminations and process preemptions. So later on, you're going to go deeper one by one for each of the methods. So let's see one by one. First of all, we're going to look into prevention. We try to prevent the deadlock to happen. So the deadlock prevention ensure that at least one of the necessary condition for deadlock does not hold. So can be accomplished by restating the way requests can be met. So you already look into there is 4 mutual exclusion, which is must hold for non-shareable resources that can be accessed simultaneously by various processes. So you can have various processes to have a non-shareable resources, therefore cannot be used for preventions under your mutual exclusion. Hold and wait must guarantee that whenever a process requires resource, it does not hold any other resources. Example here, first, require process to request and allocate all resources before it begin execution, and or is going to be allow process to request resources only when process has non-allocation to it. And another one still under hold and wait, which is low resource utilization, which is there will be a possibilities for starvation to occur. So we can conclude that on the deadlock prevention method, to do deadlock prevention, we must not allow at least one of these conditions. So you're not going to allow must not allow at least one of these conditions, which is mutual exclusion, whole and wet, no preemptions, and also circular weight to happen at the same time. So you cannot uh, run it or allow it to happen in similar time. We have another two, which is non-preemption, preempted, and also circular weight. For non-preemptions, it is not practical for most systems. Whenever it's happened, if a process that holds some resource requests another resource that cannot be immediately allocated, then all resources currently being held are released. Preempted resources are added to the list of resources for which a process is waiting, and process will be restarted only when it can regain its own resource, as well as new resource that you are or a process requests. Well, for the last one, which is the things that you cannot allow it to happen, which is circular weight, which imposes a total ordering all resource types and require all that each process requests resources in increasing order of enumerations can be used in practice. So this is the four things, and you can conclude it in a shorter way, which is under mutual executions. Only one process at time can use resource. Hold and wait. Process hold resource while waiting for others. No preemption. If a process has resource, it cannot be forced to give up or cannot take a resource away from the process. And lastly, circular waiting processes form a cycle. So this is the four things under that you need to prevent the deadlock, the things that you need to know. So here is example when you have two bank transactions, 1 and 2, execute concurrently. Transaction 1, transfer $25 from account A to account B. So transaction 1, this is transaction 1. So you have $25 you transfer to B. While for transaction 2, it's transfer $50 from B to A. So this is the deadlock example with log ordering. So you're going to have a simple or general problem how you're going to write a program. So let's say here you have a account 2, which is the account, of course you have 1 and 2, which is A and 2. Transaction A 1 and 2, log 1, log 2. So where you're going to transfer to and how much the amount you're going to transfer. So this is just a general example for you to use if we have two transaction like this, and whether it's going to wait for a B transaction 1 to finish first and it continues for transition 2 or not. You're going to prevent a deadlock. So I guess it is not too many. For this module 7, you have another half. So I'm not going to finish it all. After this, you're going to continue with another 3 methods. Where is it? Okay, just now you look into the preventions about what is the meaning of all these 4 conditions. And later on, you're going to see avoidance, detection, recovery, and how you're going to also ignore. So we're going to discuss it in our next class. You can see a lot of example. If you have a lot of processes to happen, how you're going to detect. There is a detection algorithm under detection and deadlock detection. Later on, you're going to see also on the recovery after you already done and cure the deadlock, how you're going to recover. And the rest is just for you to see here in terms of the example under under the deadlock avoidance algorithm. It's quite many because you're going to see on the banker algorithm. Banker algorithm also there is 2, safety algorithm and resource request algorithm. That's why it's quite many. So we're going to continue later on the deadlock avoidance in our next class. Is it okay? Because I think you can take your time to understand the basic process first for the deadlock, and you just already come out with one solution, which is the prevention for the algorithm. So later on, we will continue with another algorithm in our next class. Okay, so you have still have time for you, for those who still not yet finish lab 2, you can try to do it. You have another like 15 more minutes to finish our class, so maybe you can try to continue. I don't want to have any extension anymore. For lab 2, it's not coming out to your task 2. I already confirmed with the coordinator. There is no relationship between your task 2 with your lab 2. So I guess it's not any critical things in your lab 2. So you can just submit it. I guess if you submit, because yesterday some of your friend also asked me several questions. Then after finish discussion, I look into the schema back. Then I understand some of things might be if you submit quite different, especially in terms of the program. So I will try to understand. I will try to run. If it is okay, then I can give you direct full mark, although it is not similar to the schema. Okay, no worries about your lab 2. So I guess only until here for this today class. Scan your QR code here. For the rest, you can leave. Thank you and stay safe. Meet you again next week. Bye bye.
Dokter.
Okay. Yeah.